All right, so before we get started, first of all, I have your exams graded. I have not posted your scores yet. I'll post those right after class today. You can come view them in my office hours this week or next Wednesday. All right, so May 7th, Wednesday. That's when we'll have an exam viewing here. I won't be taking attendance. It is optional. But I will have exam 1 and 2 for you to come and look through on Wednesday. Importantly, on Monday of next week is your exam 3. All right, and Monday is the only day that it's available in the testing center. Typically, I had been able to book 2 days for your exams. This particular exam, that last week, is a little bit more of a schedule crunch in the testing center, so that I was only able to book that 1 day, that first Monday, okay? In class, if you can make it, we'll be doing a review session, or you can use that time to take your exam. I won't be taking attendance on Monday of next week, right? You can use that time to take your exam in the testing center. Cool. All right, so we got one more chapter to cover here. I know everybody console yourselves. We're on our last chapter of organic chemistry. It's very depressing. All right, but we got one more to finish it up here. This is what we call alpha carbon chemistry. All right. And as your kind of daily quiz implied here, we're actually going to go back to aldehydes and ketones, but talk about a different aspect of them. All right, so let's just get an example molecule down here. All right, we'll take a look at this this aldehyde. All right, and everything that we studied about this functional group previously all relied around this carbonyl carbon here. And we know, because I've drilled it into your heads, that this carbonyl carbon likes to play the role of what in a chemical reaction? Electrophile, right? So that's what we've learned about our aldehyde and ketone chemistry up until this point, is we have that electrophilic carbonyl carbon. And that is true, right? It's not like I lied to you. That is definitely an electrophilic site in that functional group. Okay? But we also are now going to look at a different portion of this molecule here. All right, what we call the alpha carbon. All right, the one removed from that carbonyl carbon. So when they have an aldehyde or ketone, that carbonyl carbon, they start numbering away alpha, beta, gamma, epsilon, I don't know my Greek alphabet. Anyways, they start labeling those carbons as they go down away from that carbonyl carbon. The one right next door is the alpha carbon. And this is going to be our focus of this chapter here. All right. It turns out that that alpha carbon is relatively acidic. Not crazy acidic, like you put it in solution and it drops the pH kind of acidic. But what I mean by acidic here is that it will donate that proton, or rather, you can easily, put that in quotes, not crazy easily, remove that alpha hydrogen. Okay, so the hydrogens on these alpha carbons, you don't need anything crazy strong of a base to remove it. And that's very notable because most carbons hold on to their hydrogens extremely tightly, right? The least acidic thing in the world is a carbon with its hydrogens on there. Very difficult to remove unless it's in this alpha position right here. There's something special about being in that alpha position where now we can remove a hydrogen from that carbon relatively easily. All right? So let's just go ahead and do it real quick. Let's see our acid-base reaction. draw my my alpha carbon hydrogen bond here explicitly. All right, and I'm going to use some base here. We'll talk a lot about bases, specifically what base we need to use, what strength of base, etc. For right now, I'm just going to leave it as generic B. And we're going to show that alpha carbon being acidic, right? Donating that proton. All right, and so what we're left with here is now a carbanion, a negative charge on that carbon. All right, so why are we able to remove that hydrogen from that specific location as opposed to its next door neighbor, right? Why didn't we remove it from the end here? Okay, if it's a relatively acidic proton, that means that there has to be something stable about this conjugate base here. And what makes this conjugate base so stable is that it has that electron withdrawing carbonyl group there. So we can draw a resonance structure that shows that that negative charge is being stabilized by that carbonyl group, right? We can pass that negative charge on to that oxygen atom. Remember, anytime we can draw multiple resonance structures, that's helping to stabilize that charge by distributing it across multiple atoms. So we can draw these two resonance structures here. All right, and so we're going to note, and it's going back and forth between these here. We have resonance stabilized that negative charge. Okay. This thing right here is going to be a very important intermediate in our alpha carbon chemistry. So we give this thing a fancy name here. This is what's called the enolate ion. All right, remember an enol was when you had a double bond next to a hydroxyl group. So the enolate is when you have this double bond next to a deprotonated hydroxyl group. All right. Importantly, these two are always in resonance with one another. So even though the name is named after this resonance contributor right here, you want to make note that it's really encompassing both of these structures. These are always in resonance with one another here. And in fact, usually the more useful one in our mechanisms is going to be this one here. All right. Because this one shows that this carbon has a lot of negative charge, right? It's got this electron-rich area right here, which means what can we say about this alpha carbon if it's electron-rich? Could it be a nucleophile or an electrophile? A nucleophile, right? The electron-rich one. And so that's the kind of interesting thing that we're going to note about our carbonyl chemistry that's going to be very different from what we saw previously. Previously, our aldehydes and ketones were always playing the roles of electrophiles at that carbonyl carbon. Now we're going to see that because that alpha hydrogen is relatively acidic, they can be nucleophiles at their alpha carbons. So they have electrophilic site, that carbonyl carbon. Right next door is a nucleophilic site, that alpha carbon. Cool. All right, so we're going to sort of rewind back to something that was talked about way back when you were talking about alkyne chemistry. All right. what we call the ketoenol tautomerization. All right, let's take a ketone. We'll do a simple ketone like acetone. Okay, this is always in an equilibrium with what's called an enol. So here's our ketone in equilibrium with what's called an enol, where we have those same 3 carbons. But now we have this carbon-carbon double bond. And we have this carbon-oxygen single bond. Okay. We're going to note that for all but the smallest aldehyde out there, formaldehyde, this equilibrium here generally favors that ketone form, right? So there's always this equilibrium occurring, this enol ketone conversion here, but it tends to favor the ketone form. So if you froze time at any moment and zoomed on in and started counting, you would find the vast majority of your molecules are in this ketone form with a very, very small subset in this enol form. And this is what's called a tautomerization, which is an internal rearrangement. All right, so there's no chemical reaction occurring between 2 reactants here. You're just rearranging the atoms in this molecule. If we looked at our chemical formula here, this acetone, C3H6O. If we did our enol, our chemical formula, C3H6O, right? So we haven't lost any protons or gained any carbon, none of that. We've just kind of reorganized our bonds here. All right? So first of all, what bonds are we breaking in our ketone? Does anybody see one?
Carbon-oxygen pi bond.
Yeah, we need to get rid of this one over here because we're going to make a new carbon-carbon bond over here. What other new bond are we making on the product side? This one here. All right, so what bond am I breaking on my reactant side that I'm missing here?
Carbon-hydrogen.
Yeah, so let's note how many hydrogens live on this carbon compared to how many hydrogens live on this carbon, right? So we're moving our hydrogen from over here. These are our 2 bonds that we're breaking. We're moving that hydrogen up onto that oxygen over here. These are the new bonds that are formed. All right, and it's going back and forth and back and forth and back and forth between these 2 conformations here. Majority of the time living over here in this ketone one, but we're going to see this enol conformation is still pretty important. All right, so I want you to see if you can't work out here what this would be mechanism-wise if we had this under acidic conditions. Under acidic conditions where we're going to use the proton donor hydronium and the proton acceptor under acidic conditions, it's going to be water. All right, see if you can't do this mechanism to take us from A to B here. Make sure to follow those rules for acidic conditions. right, so we're going to have to protonate that carbonyl oxygen. That way when we break that pi bond, we don't have any negative charges. Let's scrunch this up here. Okay. What would not be the biggest sin in the world, but it doesn't actually occur, so let's talk about this because I saw this in a lot of people's exams, was the next step of this right here, all right, where we break this carbon-oxygen pi bond. That puts this pair of electrons up here and gives us this carbocation intermediate. This does not actually occur here, all right? And again, it's not the greatest sin in the world because you do have only positive charges. You don't have any strong base there, all right? So this is a great partial credit answer right here. But again, it doesn't actually occur. This step is not favorable because carbon, these carbocations, only form in the rarest of circumstances. They're much higher energy than this intermediate over here. Because notice on this left-hand side, my oxygen still has its complete octet, right? A carbocation is extra high energy. Not only does it have that net charge, it also has an incomplete octet, right? So we don't form these carbocations that just kind of sit there and chill. This pair of electrons would much rather sit down here. We do need to break that bond. It just doesn't happen in these two distinct intermediates here, right? So instead, in order to break that bond, we're going to have to keep carbon's octet satisfied using that pair of electrons from my carbon-hydrogen bond. So we need this base over here in order to remove that hydrogen. All right, so this kind of E2-ish mechanism here where we get rid of that hydrogen, remove that hydrogen, reform that carbon-carbon pi bond, or rather form that carbon-carbon pi bond, and break the carbon-oxygen pi bond all in one shot here. Cool. All right, so it's bouncing back and forth between these two conformations here. Cool. All right, and this is going to be important towards understanding our reactions here. The idea that, yes, it doesn't spend much time in this form here, all right, but nonetheless, we're going to start talking about these reactions at our alpha carbon, all right, and the first one is a halogenation reaction. All right, so if we take an aldehyde or ketone, we can treat it with a halogen like bromine under acidic or basic. We're going to see both. So actually, let's just note here, this first one is acidic conditions. We're going to halogenate this ketone here, but specifically at that alpha carbon. Well, all right, so under acidic conditions here, if we have our ketone under acidic conditions in the presence of that halogen like bromine, we're going to see a reaction between our ketone and our bromine at that alpha carbon, all right, where we halogenate that alpha carbon position. Okay, so let's take a look at our mechanism. All right, I'm going to be kind of lazy here and just show that our first step here is going to be that keto-enol tautomerization that we just did. Right, so why that ketone reacts with that halogen, it actually first forms our enol here, and our enol is what reacts with that halogen. Okay. Okay, so that carbon-carbon double bond, we've seen alkenes play the role of nucleophiles before, including with halogens, and that's exactly what happens here. That carbon-carbon double bond is going to play the role of the nucleophile and grab that bromine. All right, so everybody take a second and draw me what my intermediate would be. All right, one more thing, one more step here. This pair of electrons, actually, let me sort of take a step back. Here we go. So if I followed these electron pushing arrows here, this would be my product, right? And we also got a bromide ion, this inorganic ion floating around. All right. For the same reasons that we were discussing before, this isn't what we want to do in our mechanism. This accomplishes all the right goals in terms of bond making and breaking, but there would have been a more stable way to do this here. Because again, if I look, I have this carbocation that's formed here. And again, carbocation is very high energy because we have this incomplete octet. So the way to stabilize this here would be to instead put that positive charge on that oxygen. This is a much more stable intermediate here because now I still have that positive charge. I don't have that extra pair of electrons, sorry. I don't have that positive charge anymore, or rather I still have that positive charge, but it's now on this oxygen which has a complete octet versus a carbocation which would have an incomplete octet. All right, so that's why we're going to have this as our intermediate. That pair of electrons on that oxygen will come down and satisfy that carbocation. So then we got one more step here, which is to just get rid of this hydrogen. We're going to need some base to do it. A lot of places might show this bromide ion playing the role of a base, but that is an absolute trash base. So really what's going to be playing the role under our acidic conditions is going to be water. So at the end, we have halogenated the alpha carbon position of that aldehyde or ketone. All right. So under acidic conditions, you get one halogenation event that occurs here, okay? We're going to talk about the regioselectivity of this reaction. All right, by that I mean in my previous example, I had this symmetric aldehyde or my symmetric ketone. So whichever alpha carbon I chose, I would have gotten the same product. Well, let's take a look at this one. right, so in this one here, I would have two possible products that I would get. One by halogenating the alpha carbon on the left, and the other by halogenating the alpha carbon on the right. Okay, and it turns out we don't get this 50-50 mix of these two products here. One of these is going to be favored over the other one. One of these is our major product, and one of these is our minor product. All right, so in order to figure that out, let's think about this here by looking at the intermediate, that enol intermediate for each one of these products. Right, in order to get this product here, this orange product, my enol intermediate, right? Remember, it's that carbon-carbon double bond that's playing the role of the nucleophile. So that means that carbon-carbon double bond must have formed over here on the left-hand side. All right, so here was the enol that I would use in my mechanism to form that one on the left. All right, everybody take a second and give me that enol intermediate that you would need to form this one over here on the right. Well, my major product here will be the one with the more stable intermediate, right? So then which one of these is going to be my more stable intermediate, the orange or the blue? The blue, and why is that? More substituted, right? So the more substituted alkene, that implies that it's more stable. All right, so we can see that our major product here will be where that bromine is added to that more substituted carbon. All right, that's my more stable intermediate, enol intermediate that will form. All right, if we do the same reaction, we can actually do the same reaction under basic conditions. All right, then our intermediate isn't that enol, but a deprotonated enol, that enolate. Right, and remember that's these two forms that are in equilibrium with one another. Kind of the namesake, the enol that's deprotonated. But again, what's going to be sort of even more helpful is it really shows that nucleophilicity of that carbon. It's that carbanion form, right? So this is this enolate intermediate. Right? It turns out that this enol that forms under acidic conditions once you brominate that alpha carbon, you don't form any more enol. You now shift this equilibrium way in favor of that keto form. Under basic conditions, once you brominate that alpha carbon, it will form an enolate even easier. All right, so it turns out that under basic conditions, this reaction doesn't just stop with a single bromination event, but rather all of your alpha hydrogens will be replaced with bromines. So we took this ketone here, 3-pentanone, and we treated it with bromine under basic conditions. We would fully brominate those two alpha carbons. All right, it's going to bother me how ugly that is. Not much better. Anyways, all right, so under basic conditions, we have a different intermediate. All right, and we're going to note that we replace all alpha hydrogens with that halogen. All right, so we're talking about this alpha carbon halogenation here. We have acidic conditions where we have to keep in mind our regioselectivity of our reactions. Under basic conditions, we're going to see that we fully brominate that alpha carbon, so we replace all of our alpha hydrogens with bromines. All right, and the last one that we're going to kind of look into more specifically is what happens to methyl ketones. Under these basic conditions. All right. So first, we do get exactly what we saw before. So this is a methyl ketone because on one side of that carbonyl bond is just a methyl group, right? So this is a ketone where that carbonyl carbon is specifically on the second carbon, okay? So what happens first is kind of what we would expect based on what we discussed. We brominate that methyl group, and it gets fully brominated because it is under basic conditions here. All right, but once this thing forms here, something else happens that's a little bit different, which is we have these basic conditions. So we have these hydroxide ions flying around, right, floating around. And we know that hydroxide is a good base, but also a good nucleophile. So what happens here is we get this nucleophilic attack on that electrophilic carbonyl carbon. This forms our intermediate, our tetrahedral intermediate. All right, and normally we wouldn't be really concerned about this here, because when we get our tetrahedral intermediate, what question do we ask ourselves? Is there a good leaving group? And normally the answer would be no for an aldehyde or ketone, because we can't really kick off carbons or hydrogens. All right. An exception, though, is when they are bound to three halogens. All right. So although carbon by itself, that methyl group isn't a good leaving group, once it's replaced with all these bromines, now it is a good leaving group. So now that pair of electrons is going to come down, and it's going to kick off that good leaving group, leaving me with a carboxylic acid. All right, or really, since I'm under basic conditions, should probably show that it would be not its carboxylic acid form, but a carboxylate. We're just going to note, really, that carboxylate ion. I was going to be lazy. I guess I'll show it. All right, we have hydroxide floating around. That means this acidic hydrogen here doesn't stand a chance. And this thing will not continue to react with bromine at its alpha carbon, because the alpha carbon of this carboxylate ion is no longer nucleophilic. All right, you can't take that hydrogen off of that carbon anymore. It's not going to be able to be stabilized by this carbonyl group. This carbonyl group is already doing some work trying to stabilize that oxygen, right? You'd have a net charge of -2 in that organic molecule, which you're just not going to see. All right, so if instead we start with a methyl ketone, these get converted, not halogenated, but converted to carboxylic acids. All right. So now we're going to start in on, and what we'll pick up with next time, what are called aldol addition and then condensation reactions. All right, so if we take our aldehyde and our ketone, in the presence of hydroxide, we're going to get this reaction that occurs between aldehyde molecules. All right, so on my reactant side here, I'm going to draw a second molecule of that aldehyde. Okay, what we're going to see is that one of these is going to play the role of the nucleophile at its alpha carbon. And the other one's going to play the role of the electrophile. Where's the electrophilic site? That carbonyl carbon. All right, so this is now between neighboring aldehydes in this solution here, or in this mixture, where one of them plays the role of an electrophile and the other one plays the role of a nucleophile. Okay, so what's going to happen is we need to create this nucleophilic alpha carbon here. We're going to deprotonate that under our basic conditions. Get rid of my hydrogen. Now I got a negative charge on that alpha carbon. Again, that's my nucleophilic site here. All right, so again, one of these is going to be playing the role of the nucleophile. One of them is playing the role of the electrophile. After we create that enolate ion, that negative charge, that pair of electrons, is going to attack that electrophilic carbonyl carbon. That'll bump that pair of electrons up onto that oxygen. All right, so I'm going to try to keep my color consistent here. All right, and I'm also going to kind of arrange this on the page in a similar way to how it was in the previous step, so that we can more easily see how these two molecules are being connected here. We have the alpha carbon of my nucleophile connected to the carbonyl carbon of my electrophile. Okay. And then the last step here is just a proton transfer to protonate that. Okay, and so we get this product over here. This is what they call an aldol, because it's got an aldehyde section and an alcohol section. All right. I will note that even if you used instead a ketone, they still call it an aldol, even though there's not an aldehyde group in there. All right. So this is our reaction here that takes place between these two aldehydes, where one of them plays the role of the electrophile, the other one plays the role of the nucleophile at its alpha carbon. And so we get this new bond between these two molecules, our alpha carbon of one and that formerly carbonyl carbon of the other. We get that same tetrahedral intermediate that we've seen before, and we protonate that to form our alcohol here. All right, so what was formerly your carbonyl carbon here now is got an OH group on there instead of that carbon to oxygen double bond. So real quick, one way to make sure that we form this correctly, a little trick that you can use to make sure that you've linked these two molecules up. Always count your carbons, right? So this reaction is going to kind of suck in that we're making a new carbon-carbon bond, so we're necessarily getting a big ugly product on the other side, right? Count carbons to make sure you have the proper number of carbons. The other thing that you'll see is the spacing of these two functional groups is always the same if you've done your product correctly. If I'm starting to count from that carbonyl group, I got 1, 2, 3 carbons between those two functional groups. And that will always be the case because how these are linked up here. So that's just a really easy double check when you get done. Make sure the spacing of those two functional groups is that 3 carbon spacing. Cool. All right, we'll pick up with this next time.